Hi, let us see how to find the eigenvalues and eigenvectors for a 2 by 2 matrix. We have seen how to find the eigenvalue for a 2 by 2 matrix, and we'll place the link in the description for that lesson. So let's go ahead into the eigenvectors, the eigenvalues and eigenvectors for a 2 by 2 matrix. Now we have this matrix, it's a square matrix, and we are to find the eigenvalues and eigenvectors. In our last lesson, we noted that when we have x to be equals to lambda x, by the time I place ax minus lambda x becomes 0, the characteristics equation from here will be a minus lambda into I. Determinant of this should be equals to 0. I explained this extensively in our last lesson. So based on this notion, we would also is 4, 3, 1, 2 minus the identity matrix, which is 1 and 0, 0 and 1. Remember, when you are constructing your identity matrix, and here will be my lambda is equals to 0. Remember, when you are constructing your identity matrix, the major diagonal contains ones. Now, so that this now can be written as 4 again, 3, 1 and 2 minus. Now I have lambda multiplying my identity matrix 4, 0, 0 and lambda to be equals to 0. So finally I can now rewrite this in the form of, here will be 4 minus lambda, and here is 0, here is 3, then here will be 2 minus lambda. Sorry, here is 1. 1 minus 0 is 1. 1 minus 0 is 1, not 0, is equals to 0. But for our characteristic equation, remember that is the determinant of the matrix that is actually equals to 0. 1 is 2 minus lambda is equals to 0. Now we'll now find the determinant of this matrix, so that this becomes 4 minus lambda into 2 minus lambda minus 3 is equals to 0. In case you missed our lesson where we explain determinant of a matrix, we would place a link to that lesson in the description below. Okay, let us open the bracket. Let's open the bracket. It becomes 4. I have this into 2 minus lambda minus lambda now. I have it again into 2 minus lambda minus 3 is equals to 0. So that 4 times 2 is 8 minus 4 lambda minus 2 lambda now minus lambda squared. Okay, minus lambda times 2, that's minus 2 lambda, minus lambda times minus lambda, that's plus lambda squared, minus 3 is equals to 0. Let's rearrange. We'll rearrange, and we'll collect like terms. We'll collect like terms. So that in rearranging, I'll prefer to place my lambda squared in front. Minus 4 lambda minus 2 lambda, that's minus 6 lambda, plus 8 now minus 3. Okay, plus 8 minus 3, that's plus 5. That's plus 5 is equals to 0. So that lambda squared minus 6 lambda plus 5 will be equals to 0. Then we can now factorize this to get the actual value of lambda. Lambda times lambda, 5 times lambda squared, that's 5 lambda squared. So I will have lambda squared minus 5 lambda squared is the same thing as the factors of 5 lambda squared can be minus lambda times minus 5 lambda. I'm choosing this because minus lambda plus, I'm choosing this because minus lambda minus 5 lambda is minus 6 lambda. Minus lambda minus 5 lambda plus 5 is equals to 0. So now let us further factorize this equation. Here again is the our equation. As if I'm bringing out lambda here, I'll have lambda minus 1 left. Then here again, I'll have minus 5. Then I'll also have lambda minus 1 again left to be equals to 0. Okay. Oh God, so that if lambda minus 1 is equals to 0, obviously lambda will be equals to 1. And if lambda minus 5 again is equals to 0, obviously lambda will be equals to 5. So at this point, what we have come up to it, we have gotten the eigenvalues. We have gotten our eigenvalues to be 1 and 5. Now we're now going to find the eigenvectors for each of these eigenvalues. Now let's solve for 1 first. Now let's find when a lambda is equals to 1. Remember our equation says ax is the same thing as lambda times x, where our a is our square matrix and our lambda is our scalar. In this case, our lambda is 1. So that I can bring back my square matrix, which is 4, 3, 1, and 2. Is multiplied by x, which is our eigenvector, x1, and let's tag this x2, to be equals to our lambda, which is 1, of course, into x again, x1 into x2. Now, an easy way to interpret this is to change this matrix into a set of linear equation, so that I'll have 4x1 plus x2 to be equals to x1. Then I'll have 3x1 again plus 2x2 to be equals to x2. Now, it depends on any of the two equations you use, you definitely come out with the same thing. Now, but let's pick equation 1 first. If my 4x1 plus x2 is equals to x1, I can easily move, let's collect like terms. Let's collect like terms. So that x2 is the same thing as x1 minus 4x1. Obviously, x2 is the same thing as minus 3x1. Now, from here, I'm going to deduce my eigenvector. If I do the same thing, like I said, if whether you use equation 1 or you use equation 2, it's all the same thing. If you had used equation 2, let's use equation 2. Look at this. This is 3x1 plus 2x2 is equals to x2. Now, I want to collect like terms. My 2x1, x2, I'll bring x2 here, minus x2 be equals to minus 3x1. 2x2 minus x2, that's x2 is equals to minus 3x1. This is minus 3. Obviously, you see that what we have deduced again is the same thing. Now, what this tells me, let's interpret this expression. Let me bring up the expression again. This is x2 is equals to minus 3x1. It might be a little dicey, but I want you to understand it well. This tells me that for every one of x1, x2 is 3 times of x1. That is, x1 is equals to k, the value you should have in x2 will be minus 3. For example, equals to 5. That is, the value I'll have for, if x1 is equals to 5, the value I'll have for x2 will be the same thing as minus 15. That is, for every one of x1, you have 3. 3 of it will give you your x2. So we can now write it in vector form this way. This is x1. Let's write it in vector form. This will be 1, and this will be minus 3. Now let's solve when lambda, we have treated when lambda is equals to 1. Now let's solve when lambda is equals to 5. When lambda is equals to 5, once again, remember we said ax is equals to lambda x, so that my A obviously is my matrix x1, x2 to be equals to my lambda here is 5 into x1, x2. So that obviously I'll have 4x1 minus x2 to be equals to 5x1. And I'll have 3x1, oh, plus, sorry, this plus x2, that's plus 1, 3x1 plus 2x2 to be equals to 5x2 again. Let's just use equation 1. 4x1 plus x2 is equals to 5x1. So that, let's collect like terms. Here is x2, now will be equals to 5x1 minus 4x1. Invariably, x2 is equals to x1. This is pretty straightforward. The values are the same, so that for every one value of x1, you have one value of x2. So that my x2, which is my second eigenvector, be 1 and 1. With this, I hope you understand how to work with eigenvalues and eigenvectors. In case you missed our lessons where we started with eigenvalues, I'll plead you either look at the end screen or use the description below. And also, to ensure you receive our lessons anytime we create them, please do not hesitate to hit the subscribe button. That way, you'll be sure to get notification anytime we create our lessons. Thank you for staying with us, and see you in our next class.